Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
I want to start today with a question that the research poses right up front. And honestly, when I first read it, it sounded almost like a riddle.
Oh, yeah?
What if the single biggest headache facing industrial manufacturing, the massive, messy, expensive nightmare of waste, was actually its greatest untapped goldmine?
It is a provocative way to frame it, isn't it? And in the world of biomanufacturing, which is what we are digging into today, that is not just a metaphor.
Right.
The sources we're looking at argue that this is literally this central engineering challenge of the next decade.
And that is exactly where we are going today. We are looking at a stack of research on something called circular biomanufacturing. Now, before we get into the weeds, I have to confess something. When I think of biomanufacturing, using fermentation to make chemicals or medicines, I automatically think green.
Sure.
I think sustainable. Biology, right? Biology recycles everything.
That is the trap. It really is. It's the most common misconception in this whole field. We tend to view anything bio-based as inherently circular.
But it's not.
But the reality check from these papers is pretty stark. Most industrial biomanufacturing today is still incredibly linear.
Linear, as in the old school take, make, waste model.
Unfortunately, yes. You put high-value inputs in one end, pristine sugars, clean water, all of it.
The good stuff.
The good stuff. And you get your specific product at the other. But along with that product, massive amounts of, potential leave the factory as what the industry calls aqueous stillage or spent biomass.
Aqueous stillage is a very polite way of saying industrial sludge.
It is essentially a soup of leftovers. And right now, in a linear system, that soup is a liability. It costs money to treat, money to dispose of.
So the mission of this deep dive is to explore how we flip that script. We aren't just talking about recycling, like tossing a can in a bin.
No, this is much bigger. We are talking about a fundamental shift in the whole system architecture.
So redefining the factory itself.
Precisely. The core argument here is that we need to stop seeing waste as trash and start seeing it as a design failure.
I love that phrase, waste as a design failure. It implies that if there's stuff left over, you didn't finish the job.
Or you built the wrong machine in the first place. The goal is circular biomanufacturing, where we convert those leftovers into actual value.
Okay, so let's unpack that. The research has a very specific definition of waste that I found really sticky. It says these streams are compositionally rich, but specification-poor.
That is the core aha moment for me. If you look at that sludge, it's not that it lacks value. It is full of carbon, nitrogen, all sorts of molecules. It's rich.
It's got all the building blocks.
But, and this is the key, it is specification-poor. That means it's dilute, it's variable, it's tangled up with impurities. It doesn't meet the strict specs you'd need to just reuse it.
It's messy.
It's very messy.
So it's like you have a garage full of valuable antique car parts, but they're all mixed into a giant pile of mud and oil. The value is there, but you can't just reach in and grab a carburetor.
That is a perfect analogy, and the research highlights 4 specific categories of treasure hidden in that mud.
Okay, let's break those down. First one is convertible bulk carbon.
This is the fuel, residual sugars, polysaccharides. In many fermentations, the carbon source, the food for the microbes, is the single biggest cost. Throwing that away is just burning money.
Okay, so that's the energy. Number 2 is recoverable nitrogen and protein. Where's that coming from?
From the microbial biomass itself. Remember, you are growing billions of bacteria or yeast cells. When you're done, those cells are often just waste, but they are packed with protein.
We'll get to some examples later, but it's basically turning the tiny workers into food.
In a biological sense, yes. Then you have the third category, functional fractions.
This sounds expensive.
It can be. These are things like pigments, lipid specialty molecules that might only be there in tiny amounts, but they have a very high unit value.
The diamond in the rough. And the fourth.
Inorganics. Salts and nutrients. It sounds boring, but it's critical. They're expensive to buy and a pain to treat if you dump them. If you can loop them back, you solve 2 problems at once.
Carbon, protein, fancy molecules, and salts. But you can't just scoop them out. The research talks about a strategy called cascaded utilization. What's the logic there?
Think of it like a hierarchy. You don't want to take a beautiful mahogany table and just burn it for heat, right?
Right, you'd use as a table first, its highest purpose.
Exactly. Cascaded utilization means we design the system to recover the high-value, fragile stuff, those functional fractions, first before they degrade.
Get the diamonds out before they get crushed.
Then you use the bulk leftovers, the sugars, the fiber for something else. You cascade down the value chain.
That makes so much sense on paper. But, and there's always a but, if the chemistry is there, why isn't every factory doing this?
Because it is incredibly hard. This brings us to the engineering bottleneck. The sources emphasize this isn't really a technology problem anymore. It's a systems complexity problem.
The logistics of the loop.
Right. And there is this fascinating tension between two concepts, process intensification and circularity.
Okay, let's pause on process intensification. What are we talking about here?
In engineering, it's about making the reaction itself work harder. Extreme optimization. You're trying to control every microscopic imbalance to make the main process as efficient as possible.
So you're tuning a race car for a perfect performance on a perfect track.
That's a great way to put it. But here's the trade-off. The more you intensify a system, the less robust it becomes. It's like a Formula One car, incredibly fast. But if it hits a pothole...
The whole thing shatters. And waste streams are basically nothing but potholes.
Exactly. Circularity introduces chaos. Waste streams vary, they have impurities. So if you feed that messy circular fuel into your hyper-optimized engine, the whole thing can just break down.
That is such a critical insight. We've spent 50 years making these factories into precision instruments, and now we're asking them to eat garbage. You can't just do that.
You need bouncers at the door. You need separations.
Right. And the research points to two main technologies here. First, membranes.
High-tech filters, basically. Ultrafiltration, nanofiltration. They're used to concentrate proteins or polish recycled water, but the enemy of membranes is fouling.
Clogging.
It's worse than just clogging. Because waste streams are so messy, they form this slime layer on the membrane almost instantly, and it just destroys the efficiency.
So it's a high-maintenance relationship. What's the second technology?
Supercritical fluid extraction, or SFE.
That sounds like something in a science fiction.
It's very cool tech. You take a fluid, usually CO2, and you pressurize it until it's in a state that's halfway between a liquid and a gas.
Wait, both at the same time?
Yeah, a supercritical state. And in this state, it can diffuse through solids like a gas, but it dissolves things like a liquid. It's fantastic for pulling out those high-value compounds without using dirty solvents.
So SFE is like the sniper rifle picking off the valuable targets.
It is, but the report mentions some really painful failure modes for these technologies. My favorite is recovery without marketability.
Ouch. That just sounds like a business school nightmare.
It happens. You spend millions on the equipment, you save the chemical, but it isn't pure enough to sell. Or the market just isn't there. You saved it, but it's still effectively trash.
Or the cost of separating it is more than the product is actually worth.
Exactly. Separation cost dominates. That's the economic killer.
So if we can't just filter the waste, maybe we can get something else to eat it. This brings us to the biology part, the biological transformers.
This is where we look at engineered microorganisms, bacteria, yeast, algae. The idea is to use these microbes to consume the waste that our machines can't handle.
But again, going back to the Formula One car, aren't microbes usually pretty sensitive? You can't just throw any old yeast into a vat of industrial sludge.
Definitely not. The report details some really strict constraints. First, they need inhibitor tolerance.
Because the waste is toxic.
It can be. It often has phenols or salts that would kill a normal lab-grown microbe. So you need a bug that is tough. You need the cockroach of the microbial world, not the poodle.
A tough bug. What else?
Substrate breadth. A normal microbe might like one thing, glucose. But a waste stream is a buffet of weird sugars. You need a microbe that isn't a picky eater.
Okay, a tough, non-picky eater. And the research splits this into two paths. Upgrading versus repackaging. What's the difference?
Upgrading is alchemy. You take cheap carbon trash and the microbe turns it into a high-value chemical. You're significantly increasing its value.
Lead into gold.
That's the dream. Repackaging is more pragmatic. You're taking residues and just turning them into standardized nutritional ingredients. The classic example is animal feed.
And this is where synthetic biology comes in, right?
Yeah.
We're not just finding these microbes anymore.
No, we are building them. The term they use is bespoke catalyst design. Scientists are programming microbes to match specific waste streams.
Matching the bug to the sludge.
Exactly. They can engineer it so the microbe can handle different weird sugars. They can even build in dynamic regulation.
Dynamic regulation.
Imagine the microbe has a sensor. If the waste suddenly gets too salty, the microbe can switch its genetic gears to protect itself instead of just dying.
So it adapts in real time. That is incredible.
Mm,
But I'm guessing real life is always messier than the simulation?
always.
Speaking of real life, let's move to where the rubber meets the road. The source material breaks down 3 real-world archetypes.
Yeah, these case studies are great because they show it's not a one-size-fits-all approach.
Let's start with one that hits close to home for a lot of us. Breweries.
Beer, a classic bioprocess. But for every pint you drink, there is a huge amount of brewer's spent grain, or BSG, left behind.
Which usually just gets dumped or maybe given to a farmer for cattle feed.
Right. But BSG is a massive resource, and the research shows it can be a source of alternative protein for humans, not just cows.
How much protein are we talking?
If you process it correctly, you can get fractions that are 61 to 66% protein.
Wow. That's a protein powder supplement made from beer waste.
It is. And it's also being used for sustainable packaging, a perfect example of a high-volume residue finding a second life.
Okay, case study number 2. Pharmaceuticals. The fermentation broth waste from making drugs.
Correct. The leftover liquid after you've taken out the medicine.
That has a high yuck factor.
It really does. But the solution here is upgrading it into animal feed additives.
Why feed additives?
Because the microbes in the fermentation have already pre-digested a lot of the tough stuff, which can improve nutrient bioavailability. And this highlights a key concept called specification alignment.
Specification alignment.
The animal feed market can tolerate some variability. It doesn't need to be 99.99% pure, so you're matching a messy stream, the broth, to a market that can handle it.
It's finding a home that accepts you for who you are.
That is a very sentimental way to put it, but yes, it's about finding a market with loose specs.
Case number 3. Agriculture.
Mm-hmm.
Corn stalks, straw, all the leftovers.
This is the integrated biorefinery concept. The holy grail here is converting those residues into biopolymers, bioplastics.
We hear about this all the time, but we don't see corn-based plastic everywhere yet. What's the catch?
The catch is pre-treatment. To get the sugars out of a tough corn stalk, you have to treat it usually with high heat or acid. But, and here's the double-edged sword, if you treat it too harshly, you create chemicals that poison the fermentation.
So you release the food, but you poison the plate it's on.
That is a fantastic analogy. It's this delicate balance. You have to find the Goldilocks zone of pre-treatment.
So we have the tech, we have the bugs. Let's talk money. Is this stuff actually profitable?
And the reality check here is pretty harsh. Circularity is not automatically profitable, nor is it automatically climate positive.
Wait, hold on. Not climate positive.
Yeah.
How is recycling not good for the climate?
Energy. It all comes down to thermodynamics. If you have to boil thousands of gallons of water just to recover a tiny amount of product, you might be generating more carbon emissions from the energy you use than you save by recycling.
You're burning more coal to save a paper cup.
Essentially. The research calls for integration science. You have to look at the whole picture. You can't just assume circle equals good. You have to prove it with the math.
That's a really important nuance. Green isn't always green.
However, the drivers are shifting. Regulations are pushing this. Often, the public benefitless pollution is higher than the private profit, so governments are stepping in.
Making it expensive to dump or paying you to recycle.
Exactly. The regulatory landscape is forcing companies to look at those waste streams as liabilities that need to become assets.
So what's the big takeaway here? Where is this all heading?
It means we are moving away from this silver bullet mentality. For a long time, the industry thought, if we just find the perfect superbug, it will eat all our trash and poop out gasoline.
That'd be nice.
It would be. But the research shows the answer isn't a single organism or a single machine. It is the architecture. It's how we integrate everything.
It's the system.
It is. It's the realization that circularity succeeds when we start to design specifications for waste. We have to treat the waste stream with the same engineering respect that we treat the main product stream.
That is a powerful shift. It stops being waste and starts being product B.
Exactly. It's moving from disposal to cascaded utilization. It's less exciting than a magic microbe, maybe, but it's how the industry actually changes.
It's growing up. Realizing that cleaning up your room isn't just about hiding the mess. It's about organizing it so you can find your stuff again.
And realizing that half the stuff on the floor is actually money.
Even better. I think the final provocative thought I would leave you with is this. The bottleneck isn't the biology anymore. We can engineer the bugs. The bottleneck is the integration. We have all the parts. We just haven't figured out how to bolt them together without breaking the whole machine.
It's a whole new way to look at the world.
It really is. So the next time you look at a factory, or even your own trash can, don't just see the end of the line. Think about the design failure that put it there.
Thanks for diving deep with us today.
Always a pleasure. See you next time.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.